Hello and welcome to Quantum Foundation Unveiled. I'm Gilad Laredo. I'm an independent researcher, and on this channel I will be exploring a new option for classification of quantum mechanics, showing how the wave function can be interpreted through the lens of electromagnetism. I'll be diving into the mathematical foundations, trying to present new ideas that push the boundaries of what we know. Now note that this video is divided into two sections. The first section introduces the Schrödinger and the Dirac equation, while the second section delves into the core of my discovery, illustrating how quantum mechanics connects with electromagnetism. Now, there are numerous YouTube videos that explain the Dirac equation more comprehensively than I do here. However, the main message I want to convey is in the second part of this video. So if you're already familiar with the Dirac equation and its significance, feel free to skip to the second part of this video. Let's begin. As an introduction to this study, we'll briefly review some of the foundational concepts of quantum mechanics that emerged between 1924 and 1928. Although earlier giants like Bohr, Planck, Heisenberg, Pauli, and even Einstein made significant contributions, we'll start with Louis de Broglie's hypothesis, proposed in 1924. De Broglie suggested that particles have an associated wave with a frequency omega and a wave vector k, which are linked to the particle's energy and momentum through Planck's constant. 2 years later, Erwin Schrödinger developed what is now considered a cornerstone of quantum mechanics, the Schrödinger equation. He introduced the concept of wave function, indicated as psi, which is a mathematical description of the quantum system, such as electrons' probability density in an atom. Schrödinger's wave equation provided a successful explanation for phenomena like the hydrogen atom spectral lines, and for a short time it was thought to be the fundamental equation of quantum mechanics. However, discrepancies with experimental data led to the addition of extensions such as Pauli matrices to account for electron spin. Additionally, it became evident that the Schrödinger equation was incompatible with Einstein's theory of special relativity due to its differing treatment of time and space derivatives, first order for time and second order for space. Schrödinger himself noticed this issue and developed a relativistic version of his equation, though he decided not to publish it because it incorrectly predicted the hydrogen atom's emission spectrum. But Oscar Klein and Walter Gordon later published the same equation, now known as Klein-Gordon equation. Despite initial issues such as prediction of negative probabilities, the Klein-Gordon equation was eventually understood to correctly describe particles with zero spin, like pions. Paul Dirac was troubled by the incompatibility between quantum mechanics and special relativity. In 1928, after struggling with this issue, Dirac proposed a remarkable solution. Addressing the limitations of the Schrödinger and Klein-Gordon equations, Dirac formulated a relativistic equation for spin-half particles, which became the first successful theory to combine quantum mechanics with special relativity. In a way, the Dirac equation can be seen as a sophisticated square root version of the Klein-Gordon equation. It extends the wave function from a single dimension to a four-component vector known as bi-spinor, and introduces four gamma matrices that satisfied Clifford algebra. In the equation, the gamma matrices and the derivatives are summed by an Einstein summation convention where mu runs from 0 to 3. Unlike the Klein-Gordon equation case, the Dirac equation has only first-order derivatives, which make more sense when setting initial conditions for solving the partial differential equation. Now let's delve into the technical details to better appreciate Paul Dirac's thought process and understand how he derived his equation in 1928. For simplicity, we will use natural units, where both the speed of light and the Planck's constant are set to 1. We begin by attempting to rewrite Einstein mass-energy relation. Our goal is to introduce four constants, alpha x, alpha y, alpha z, and beta, such that we can express the right-hand side of the mass-energy relation as a weighted sum of the momentum components and the mass. Next, we square both sides of the equation. At this point, we can identify the square terms from both sides. This is the x momentum component squared. This is the y momentum component squared. This is the z and the squared mass term. For the equation to hold, all cross terms must cancel out. To ensure this, we impose the following condition. The alpha terms must anti-commute with each other and with the beta term. Additionally, from the first line of the equation, we require that the square of each alpha and beta term equals 1. Dirac discovered a way to eliminate the square root from Einstein's mass-energy relation by introducing the alphas and betas constants, where these needs to satisfy specific constraints. But what are these constants? Dirac realized that due to the anti-commutation property, these constants must be matrices. Through further investigation, Dirac found that the minimum matrix size required to satisfy these constraints is 4 by 4. Hence, alpha x, alpha y, alpha z, and beta were all chosen to be 4 by 4 matrices. Recalling the anti-commutation properties of the Pauli matrices, Dirac constructed the 4 by 4 matrices as following, using the Pauli matrices and the 2 by 2 identity matrix. However, since the Dirac equation is structured differently from the mass-energy relation, these matrices required a slight modification. Dirac introduced 4 gamma matrices defined as follows, such that these are the Dirac gamma matrices which appear in the compact form of the Dirac equation. There are several more ways to choose the gamma matrices. We've already seen the Dirac basis, which can be compactly written using the 2 by 2 Pauli matrices. Two other commonly used representations are the Weyl basis and the Majorana basis. While we won't delve into the differences in the wave function physical meaning for each representation, the key takeaway is that the underlying physics remain unchanged as long as the gamma matrices satisfy the requirements of the Clifford algebra. Let's pause here for a recap of Dirac's strategy in deriving this equation. The first and most significant step Dirac took was to use the anti-commutation properties of matrices to effectively take the square root of Einstein's mass-energy relation. He then applied the formalism of the Schrödinger equation using the wave function and its associated energy and momentum operators to write his final equation. This was done with a simple transformation of his original alpha and beta matrices. These are the essential ingredients in the recipe for the Dirac equation. Now you likely have a clear understanding of the path Dirac took to construct his equation. Let's summarize some of the key advancements of the Dirac equation compared to the Schrödinger equation. Firstly, it predicts the existence of antimatter. Spin emerges naturally from the Dirac equation, whereas it had to be added separately in the Schrödinger equation. Additionally to the spin, it automatically includes fine corrections that were manually inserted into the Schrödinger equation. The Dirac equation also provides a rather good prediction of the electron's magnetic moment, and it is Lorentz covariant, meaning it holds in all inertial reference frames. What is truly astonishing here is how pure mathematics led to new physical discoveries. However, despite its versatility, the Dirac equation is still formulated in a specific coordinate system, Cartesian. Moreover, as an equation for charged particles, it retains the terminology of the Schrödinger equation using wave function and energy momentum operators but lacks a direct connection to classical electromagnetism. The key questions I'm answering in these studies are: can the Dirac equation's physical content be generalized to be independent of the chosen coordinate system? And is there a common ontology or underlying connection between the Dirac equation and Maxwell's equations? The study shows that the answer to both questions is yes, which could enhance our understanding of quantum mechanics, quantum electrodynamics, and other quantum field theories. To provide a clearer context for the next section of this video, let's introduce a map, or a graph that outlines the foundations of physics. We'll start with the two most fundamental theories: classical mechanics that led to Newtonian gravity, and electromagnetism. In 1905, Einstein developed special relativity, building on classical mechanics and electromagnetism. 10 years later, Einstein generalized Newtonian gravity and special relativity into general relativity. In the 1920s, quantum mechanics matured, blending new ideas with classical mechanics concepts. Shortly later, Dirac connected special relativity with quantum mechanics. By now you should have a fairly good understanding of how Dirac did it. This connection, along with several more contributions, gave rise to quantum field theory, which was later formulated on a curved spacetime background. Currently, we are still searching for a unified theory of quantum gravity, with string theory and loop quantum gravity being the two most familiar candidates. Now let's organize these blocks by their shared underlying concepts, or ontologies. Classical mechanics and Newtonian gravity share the same basic framework. Electromagnetism aligns with special relativity and general relativity in its ontology. Quantum mechanics has its own framework based on the wavefunction formalism and the operator approach. Quantum field theory combines elements of both electromagnetism and quantum mechanics with new formalism. Quantum field theory in curved spacetime must also align in some way with general relativity's language. Next, we'll present that quantum mechanics and electromagnetism actually share the same ontology. This connection may be a step towards classification of quantum mechanics such that it will align with classical physics. This should result in modification in quantum field theory and raise new ideas for the unification of physics. What you are about to see next is how to describe the underlying physics of the Dirac equation using the language of classical electromagnetism. To put some physical meaning behind these words, here is the Dirac equation. As we mentioned earlier, if the gamma matrices generate the Clifford algebra, the underlying physics of the Dirac equation remains the same. By electromagnetism, we're referring specifically to Maxwell's equations. The core of this study is about constructing new gamma matrices that not only generate Clifford algebra, but also align with Maxwell's equations. And it is much more profound than it may sound. Before starting with the math, let's note the differences between Dirac's strategy and the approach of this study. Paul Dirac constructed his equation starting from Einstein's mass shell condition. He found a way to remove the square root using a 4x4 matrix formalism, and then incorporated Schrödinger's momentum and energy operators. In this study, we will construct an upgraded version of the Dirac equation. But our starting point will be to guess a different equation. We will ensure this equation satisfies the mass shell condition by applying the Broglie hypothesis. Then, we will verify that the equation set also satisfies the Dirac equation. And lastly, we will see that the equation set satisfies Maxwell's equations. If we succeed, we will have discovered a unified formalism that connects Maxwell's and Dirac's equations, creating a bridge between quantum mechanics and electromagnetism. We shall start with the following equation in natural units. The left matrix is not a standard one, as it incorporates time derivatives on its diagonal and spatial differential operators, namely divergence, gradient, and rotor. We can also see that it is an eigenvalue equation over this vector, which we shall call the S vector. This vector is constructed of 4 fields. 2 of them are real scalar fields, and the other 2 are 3-dimensional complex vector fields. Next, we will check if this equation satisfies the mass shell condition by applying the operator matrix to itself and balancing the right-hand side by multiplying with a factor of Jm. Using some vector calculus identities and eliminating terms that cancels out, we arrive at the following equation. Since the divergence of a curl and the curl of a gradient are both 0, all the red entries vanish. We are left with the following equation. It represents a set of 2 scalar wave equations and 2 vector wave equations. This can be compactly described with or without a special 4x4 identity matrix. Therefore, each field in the S vector must be a solution to the wave equation. Note again, there are 4 wave equations in total, 2 scalar wave equations and 2 vector wave equations. Since all S fields satisfy the wave equation, we'll choose the following plane wave solutions. Using the Broglie hypothesis in our plane wave solution, we can derive the same familiar momentum and energy operators. Note that here we stopped using the natural units. Plugging these operators' derivatives in our wave equation yields the following equation, which simultaneously satisfies the mass shell condition for all the fields. So we took a different path than Dirac took and found another equation that describes the cross-interaction of 4 fields, that each of which satisfies the mass shell condition. But how does it relate to the Dirac equation? Note that till now we haven't chosen any coordinate system. Let's expand the equation matrix in Cartesian coordinates. First, look how the S vector was inflated due to the full representation of the vector. Here are the divergence operator, here are the gradients, and these are the curl operators. We wish to get to the form of the Dirac equation, which is shown below. Multiplying the equation with minus j on both sides and moving the vector term to the left, we get this. Now we need to isolate the gamma matrices. And here they are, the 4 gamma matrices. We got an equation that looks like an extended 8-dimensional version of the Dirac equation. But remember that to convey the underlying physics of the Dirac equation, the gamma matrices must satisfy the property of the Clifford algebra. Well, our new gamma matrices indeed fulfill this requirement. It is worth noting that following the Dirac formalism, we can also define a 5th gamma matrix, which is mostly used in the chiral representations. And it appears to have a quite remarkable structure, with eta being the Minkowski metric. Additionally, as the Dirac equation case, the 5th gamma matrix satisfies the following commutation relation with other gamma matrices. Since all the Dirac gamma matrices relations are satisfied by the 8x8 gamma matrices, The equation can be seen as a rank 8 Dirac equation, describing fermionic field. This equation is coordinate system independent, unlike the Dirac equation, and the field vector S is equivalent to the bi-spinor psi at the Dirac equation case. Till now, we saw how this 8-row equation, that has no preferred coordinate system, is kind of an extended Dirac equation. One can ask for what is it good for, as it doubles the dimensions of the Dirac equation with no real physical benefit. We are about to see that this equation is closely related to the Maxwell equation, and this is where the real magic starts. Starting again with the original equation. Now we'll break the matrix equation row by row. This is the first row. Note that we switched back to non-natural units, where the time derivative gets 1 over c factor, and the mass term gets his c over h bar factor. Next, this is the second row. This is the third, and that's the fourth. Remember that we allow the vector fields to be complex. It means that their amplitudes are complex numbers. Therefore, we can deconstruct each vector field to a real amplitude vector field and an imaginary amplitude vector field. And yes, there is a really good reason why we chose the specific E and B notation. Substituting this decomposition in the above equations and splitting them to real and imaginary parts yields the following 8 equations. It was previously mentioned that the scalar fields S0 plus and S0 minus are real and not complex. The reason for that is that we want to have these two zeros in our equation. Therefore, we will be able to define potentials in a later stage. Additionally, note that these equations are essentially describing the underlying physics of the Dirac equations. Hence, the vague bi-spinor wavefunction terminology can be replaced by electromagnetic-like terminology. Let me repeat that. These equations are essentially describing the underlying physics of the Dirac equation. This formalism replaces the vague bi-spinor wavefunction terminology by electromagnetic-like fields with introduction of two new scalar fields, S0 plus and S0 minus. So basically we found two sets of Maxwell-like equations with the introduction of mass terms and new scalar fields, S0 minus and S0 plus. And these equations, which are not coordinate specific, actually describes quantum mechanics by replacing the wave function with somewhat better known mathematical entities, scalar and vector electromagnetic-like fields. But how does it relate to the standard Maxwell equations? Let's degenerate these equations a bit. Setting the scalar field to be equal and setting the mass to 0, and now summing the above equation row by row, we get the Maxwell equations in vacuum. Therefore, the Maxwell equations in vacuum are a degenerate version of our original equation. There are several more interesting ways to degenerate these equations. One of them leads to the Procca equation that describes massive spin 1 particles. Summarizing what was demonstrated till now, it was shown that these equations are a coordinate-free version of the Dirac equation. Instead of wave functions, we have electromagnetic-like fields. This semantic difference called for new interpretation of quantum mechanics. Additionally, the equation set can be degenerate to Maxwell equations in vacuum. Hence, it stands as a unified formalism for quantum mechanics and electromagnetism. Therefore, it is a step towards classification of quantum mechanics. You can find more developments of the theory in the linked paper at the description of this video. The paper includes the compatibility of the formalism with the Procca equation, an articulation of potentials and their gauge conditions, chirality and spin eigenvectors meaning in the new formalism, the development of a new electromagnetic-like tensor, F Monod, that describes the fermionic fields, an upgraded quantum electrodynamics Lagrangian, which is a local U1 invariant with no required gauge field patches, and compatibility of the theory with general relativity formalism, in the form of deriving stress energy tensor T mu nu of the fermionic field to act as a source in Einstein field equations. For those of you who plan to read my paper, note that the paper has never went through a peer review process, so if you're a physicist, I would be happy to get feedback and corrections if you find some bad stuff. And thank you all very much for watching, and I'll see you in the next video.